started. So yeah, so I have some large announcements, earth-shattering, course-changing announcements. So we're almost done Galois theory, and I feel like, I know for me, teaching on Zoom has been getting more and more difficult, and I've been doing a worse and worse job of like getting interaction and sort of asking questions and doing breakout rooms. So anyway, for the last 2 weeks, are gonna be on representation theory. It's sort of a new unit and sort of just pretty much self-contained. It connects to everything, but I'll just be on this thing. And so we're going to completely change how we do the class for the last 2 weeks. So we're going to, starting next Tuesday, so which is 4/13, we are going to do, we're not going to meet on Zoom anymore. We're going to use gather.town, which is a like app where you can move around and stuff. And anyway, if you've used it before, you might think this is a terrible idea, but they recently, they fixed their whiteboards. So now there are really good whiteboards in gather.town. So it actually works really well for group work. So we're going to use this for the class meetings, and it'll be a flipped class. So we'll spend the whole meeting working on problems and examples, and sort of either sort of individually in groups and discussing and so on. And so I'll post videos beforehand. So I'll post videos sort of 2 days before each class of a lecture, and I'll make the, okay, so that sounds like extra work. So let me sort of explain why this won't be extra work. So I'll post videos 2 days before each class. So this part starting for the class, not next Tuesday, but starting for the class on 4/15. So yeah, so there'll still be a lecture, but I'll just, and since I've sort of slowly stopped asking questions or like stopping to do problems, like at this point I may as well record the lecture anyway. So I'll just record the lecture and you'll watch the lecture, and then we'll sort of focus on using the class time sort of for actually working through things and sort of engaging with the material a little bit more. Right, so on 4/13, let me just say. Okay, so sorry, now I'm getting all over the place. I will post information in Canvas at the start over the weekend for how to access this. Okay, so sorry, 1 second. Sorry, all my dogs and children are trying to get into this room. Anyway, so on Tuesday, we won't start representation theory yet. So on Tuesday, sort of will be a sort of a test day just to figure it out. Test sounds bad, practice. So I'd still like everyone to come on Tuesday if you can, because we'll sort of make sure everything's working technically. So we'll sort of make sure no one's having problems like using the whiteboards or anything in this. And we'll talk about homework problems. So we'll do a little bit sort of talking in like a whole group about homework problems. I'll have you sort of present, like if you have solutions written up, I might pair you up and have you sort of present to each other so you can talk about your solutions and sort of see how other people did it. So for the current homework, so the current homework about Galois theory. Right, so, and so I'll also move the due date. So the due date, so that is more useful for you, like to have a chance to talk about the homework problems and sort of discuss with other people. Let me move the due date to Thursday. So I haven't updated on grade scope yet, but I'll update after the class, or at least over the weekend. But anyway, this is now due on Thursday, 4:15. Okay, so right, and then after that, so starting on Thursday. Yes, okay. So starting on Thursday, we'll be doing representation theory. So that means sort of like on the 13th or earlier, I'll post like a video of the lecture that you're supposed to watch before the class on the 15th, and so on. And so I'll always post the lectures 2 days before, at least 2 days before the video, before the class, so that way you have a chance to watch it beforehand. Okay, so good. And then right, and so yeah, so 4:15, 4:17, 4:20. What? That's not right. 4:15, 4:20, 4:22, and 4:27. Sorry, I'm a full-grown adult, but I still can't say 4:20 without laughing. Anyway, so on these days, we're going to so these will be all sort of on representation theory, and there will again just be, I'll just like we did for Galois theory, I'll do a single, there'll just be a single handout and homework assignment for these. And since we'll be doing, you know, I'll try and keep the homework a little bit shorter, sort of just more like sort of more interesting problems on the homework, because we'll have time in the class to do sort of to work through like more basic examples and basic exercises. So that's what we'll be doing in the class. We'll do sort of more basic examples and exercises. Okay, but so yeah, so it should be. So hopefully it'll sort of keep it a level reasonable amount of work. So that single handout / homework will be due on the 29th. So the 29th, we don't have class. But anyway, I want it to be due 2 weeks after this Thursday. So after this homework assignment's due. So that's the 29th. And then just a reminder that your final is on, I guess, the 2nd. So the 29th is a Thursday, and I better check this to make sure. Sorry, I have to look at the calendar. The 3rd, sorry. So the 3rd, which is a Monday. So you might think I could have just added up numbers to get from Thursday to Monday, but I don't know how many days are in April. So that's why I can do that. There are 30 days in April, in case you were wondering. Okay, so anyway, that homework will be due on the sort of Thursday the classes are, like Thursday, which is like the day after classes end. And then your final is on the sort of subsequent Monday. Okay, and then the last thing I think I meant to say about all of this is, and you might be wondering, well, you may or may not care, but, and it's a little bit funny, like that sort of in the first half of the class, every assignment, like you had an assignment every week, and then in the second half, you've sort of only had like assignments every 2 weeks, and you might be wondering whether those are going to be graded as 2 assignments, like, contribute to your grade as 2 assignments or contribute to your grade as 1 assignment. And since I didn't specify that beforehand, like each of these will count as sort of 1 or 2 assignments, and whatever is better for your grade. So that means sort of if you've been doing it, sort of you do worse on this assignment and the next assignment than you've done sort of the first 5 assignments, and each of these will be treated as if it was just 1 assignment. And if you do better on these ones than you sort of did on the previous assignments, then each of these will be counted as 2 assignments. Okay, so good. I think that's all I wanted to say about this change. So just to recap, because it was a lot. Starting next week, we're going to be using gather.town for our meetings, and there's going to be a flipped classroom. So sort of there'll be like discussion working on exercises and examples in class. So I'm going to post the access information in Canvas over the weekend. So on Tuesday, which is the 13th, we won't introduce any new material. We won't have like a lecture you're supposed to watch beforehand. We'll just sort of make sure everything is working, that everyone's able to access it, and we'll talk about homework problems and sort of, yeah, okay, good, but please do still come that day. And then your homework that you have right now is the due date's moved to Thursday, so that's useful for you. Okay, and then following that, we have four meetings of class left. Those are all sort of on representation theory. And so there'll be a single handout / homework for those, and lectures will be posted 2 days before, and you're supposed to watch the video sort of before the class. And then we'll just work on sort of exercises and examples and sort of in the class, like both sort of individually and in groups and sort of with class discussion. So, okay, and then the final is on the 3rd, and that will be back in Zoom. So in Zoom. The final will be on the 3rd in Zoom, and the last 2 assignments will be sort of graded in the way that it helps you the best in terms of how much they count for in your final grade. Are there any questions about all of this? Okay, great. Yeah, well, okay. Thank you for it. I think it's going to work well, and I think it'll sort of be a more useful. I hope it will be a more interesting and useful way to use your classroom. Oh, I see there's a question. I'll answer the question in a second. And either way, sort of thank you for indulging me in trying it out. Thank you in advance for indulging me in trying out this sort of experiment for the last 2 weeks, and I hope it will work a little bit better. What will be the format of the final? Thomas asked in the chat. Good question. So let me answer that now. Let me not give a definite answer because I haven't 100% decided. I think, but most likely it's going to be just like the midterm, but there'll be one more thing. And it'll be, I guess it'll be a little bit longer than the midterm because the midterm was for an hour, and like the final is, I can't remember how long the final is, but it's more than an hour. It's like 2 hours or something. So anyway, mostly, so like the midterm, but longer. Plus, I think what I'm going to do is have one problem where you write up a proof. So you have to write a proof. But like, and basically it'll be like on the homework, I will give you some options and you'll be able to pick which one you want to write up. So it won't be like, if you see like, if this just like happens to be the one problem you can't solve, you won't have an option. So I'll give you like probably 2 or 3 choices for a problem to write up a solution to. So I haven't 100% fixed on this format yet, but this is what I am tentatively planning, and maybe I'll try and figure that out by the end of next week to make sure, so that you can sort of plan accordingly. Does that make sense? Did that explanation make sense? And or are there any questions about it? Okay, so I will take that as a yes, it made sense, and no, there are no questions. Okay, so that's all of the sort of administrative business. I want to talk about solvability and radicals and sort of insolubility of the general quintic today. But before we do that, I want to do just a warm up proof. and we've already seen one argument for it, but let's give another argument for it. So the theorem is that C is algebraically closed. So any polynomial over C has a root. And so, I mean, we talked about a proof via complex analysis. And I don't think I went through the proof, but I told you could prove this using Liouville's theorem. And hopefully, if you've never seen that before, but you do know what Liouville's theorem is, then you go through that at some point. But so here I want to, and there are other proofs, but below I'll give, so below is a proof due to Artin, which is nice because it sort of uses just calculus of like the real numbers and Galois theory. Okay, so let's make when the calculus is to sort of give a key ingredient. So let me sort of state the main lemma we use. So any quadratic polynomial over C has a root. So any quadratic polynomial with coefficients in C has a root. Part one, and part two. I'm probably going to state that. I'm probably going to end up doing this proof in a suboptimal way. But anyway, let's not worry about that. So any quadratic polynomial with coefficients in C has a root, and then any odd degree polynomial over R has a root. Okay, so proof of the lemma. Well, and if you have x squared plus ax plus b, so if it suffices to give a square root of the discriminant, so in solving a general quadratic polynomial, you just make a change of coordinates, and so that reduces to solving a square root. And then sort of in polar coordinates, like the square root of r e to the I theta is equal to plus or minus like the square root of r times e to the I theta over 2. So these are the two roots of these are two square roots of something in the real in the complex numbers. So you just explicitly compute that anything in the complex numbers has a square root. So any quadratic over C has a square root. And then 2 is just the intermediate value theorem. So if you have like x to the n and so on, then for so n is odd, then sort of for x very negative, then sort of this is sort of dominated by this first term, which is negative, and then sort of if n is very positive, then again it's sort of dominated by the first term, and so it's greater than 0. So and the point is just any polynomial, like when the value is very big, is sort of dominated by its leading term. And you can make that more precise if you want, but this is sort of the idea. So if you plug in a very small value of x, you get a negative number, a very large value of x, you get a positive number. So there is some root in between. just and that's what the intermediate value theorem says. So any number in between those two, like if you're less than 0 somewhere and greater than 0 somewhere, then it's sort of some point between those 2 points, you're equal to 0. Okay, so that's those are the basic functional inputs to this proof. And now, so let's prove the theorem. Okay, so I'm going to let f be a monic polynomial over complex numbers. I'm going to sort of let k be an extension. So such that sort of f has a root in k, and I'm going to take k to be Galois over the real numbers. Okay, and so then what I'm going to deduce is that k is actually just the complex numbers. Okay, so and this is, and you might be a little bit confused. It's not like this, yeah, and depending on how comfortable you are with these things, like this might be a sentence that you have to think about for example why such an extension k exists, but I can just take any k where there's a root. So let me think. So you take any L over C finite where there's a root, we know how to make those. Then you look at L is equal to, L is now a finite extension of the real numbers. So L is equal to R adjoin alpha for some alpha by the primitive element theorem. And this is not really necessary to invoke primitive element theorem here, but it sort of shortens it, and then take K to be a splitting field of so you just take a field that has a root, and then you sort of enlarge it until it's Galois over the real numbers. That's sort of how you can produce such a thing. But then for the rest of the argument, it doesn't really matter how you got such a thing. It just matters that you can get such a thing. Although like this proof sort of does critically depend on the fact that there is an extension where this has a root. Like if you didn't know there was some extension where this had a root, everything would break down. Which is not something that was always known. Like people thought about polynomials and roots of polynomials before they when people first think about this, like they didn't know that you could sort of create a field where a polynomial had a root. And this is something we saw how to do, and it's very easy for us to do, like with our sort of modern understanding of things, but like it wasn't obvious sort of back in the day. Okay, so good. So we're gonna look at this K, and well, we're going to use the Galois theory of K. So let me write G is the Galois group of K over R. And so let me take a subgroup. Let me take a C-loft 2 subgroup. Okay. So then I'm going to look at the fixed field for that C-loft 2 subgroup over the real numbers. This is equal to the index of G and H, which is an odd number. On the other hand, I know sort of KH is equal to is sort of by the primitive element theorem, I can get sort of this extension of the real numbers by adding a fixed thing for beta in real numbers, or for beta insert in here. So this is by the primitive element theorem. So m alpha, so m beta is the minimal polynomial. So this is in a polynomial with real coefficients, and it has degree g colon h. So it has this degree of the extension, and it's irreducible. Because it's a minimal polynomials, but by definition are irreducible. So it's an irreducible element of an irreducible polynomial with coefficients in real numbers with degree g colon h. But I mean, this is odd. This degree is odd because h is a CLOF2 subgroup. So sort of h is sort of the largest power, order of largest power 2 dividing this group. So m alpha has a root, so m beta has a root. But if you have an irreducible polynomial that has a root, that implies sort of the degree of m beta is 1, since it's irreducible and it has a root. Okay, so that implies, I mean, actually, this wasn't an extension at all. Like, this was just the real numbers. And in particular, this implies that the degree of this, of the CLOF2 subgroup in G is 1. Okay, thus, so what's the conclusion? G is a 2 group, i.e. the order of G equals 2 to the n for some n. Okay, good. And so now the Galois group of K over C is a subgroup of the Galois group of K over R equals G. So that means that a Galois group of this extension C is also a 2 group. So the order, so n's order will be 2 to the n minus 1, whereas the n up here, but let me just call this 2 to the m. And this is all I need. This is all I needed to get out for this step. I needed to get out the Galois group of this field extension, K over C, was a 2 group. So now, I mean, 2 groups. Okay, so suppose, probably it's sloppy to argue by contradiction here, but let me just argue by contradiction now. Suppose m greater than or equal to 1. And of course, what I want to show is I want to show m is equal to 0. Like I want to show this wasn't an extension at all, so that f already had a root. Okay, so let me suppose m greater than 1. Then and there's a surjection from the Galois group of K over C to Z mod 2Z. And this is just the structure of nilpotent groups, or of 2 groups. And so, and if you remember, we showed sort of a 2 group was solvable. Like a P group is solvable just by sort of we use the class we used the class equation to show that its center had to be non-trivial. And then you sort of motto by the center, and then you sort of apply the class equation again to show the center is non-trivial, and so on. But if you refine this argument a little bit more, what you see is not only is a two-group solvable, like, and I say not only is a two-group nilpotent, but in really for every, like, and so just like go up this tower until the very last, like the last step, and then you're sort of getting some subgroup such that like G mod that subgroup is abelian. And then now like that subgroup has a order of power of 2, so it has a quotient that's Z mod 2Z. So okay, so that's the point. And then so okay, so that corresponds. That gives a degree 2 extension of C. Okay, but I mean, every degree 2 extension comes from, so let me say, I'm running out of letters. Call this capital M over C. So M is equal to C gamma, and then the middle polynomial gamma has degree, so this is in CX, okay, good. This has degree 2. This implies it has root. But this contradicts. This is a contradiction. That this is irreducible of degree 2. So, because we already saw that every quadratic polynomial over complex numbers has a root. That was sort of in our lemma. Okay, so this sort of gives our contradiction, and thus M is not greater than or equal to 1, so M is equal to 0. So the Galois group of K over C has size 2 to 0, which is 1, i.e. K is equal to C. Thus, F has a root in C. Okay, so this is, this is sort of a fun argument. The reason I want to sort of give this as a warm-up proof right now is because and this idea of sort of using this solvability and using sort of that you're getting certain extensions like by adjoining roots of sort of in a very specific way. Like here, like the idea that like every degree 2 extension you get by adding a square root of something. Like these are sort of the kinds of ideas that go into studying sort of solvability in radicals. This is sort of why I want to do this example now. So next up will be solvability in radicals. And what is the question? I mean, well, the question is basically, like we have a quadratic formula. So like the roots of x squared plus ax plus b, the square root. I can't remember it. What's I remember it's the square root of b squared minus 4ac. What's the other parts? Or yeah, so I choose x squared plus bc. Okay. Okay. Well, it doesn't matter, right? It's plus or minus something over something. This is the important part. Maybe it's over 2. Is it minus a plus or minus? A plus or? Can someone help me? Minus b. Sorry. Yeah, a doesn't exist, right? Okay, good, thank you. So there's a quadratic formula. Okay, so this isn't the question yet, so observation. There is a cubic formula. So you use sort of cube roots of sort of expressions and coefficients. and sort of maybe you have to iterate some things and cube roots and sort of square roots of expressions and coefficients, and sort of course, like whenever you take a cube root, there's some ambiguity because there's sort of 3 possible cube roots, just like there is sort of ambiguity here in that there are 2 possible square roots. So you did plus or minus, so this plus or minus 1. And so in here, you're really sort of allowed to use sort of 6 roots of unity. And I say it's 6 roots rather than third roots because if you have plus or minus 1, like you're allowed to use plus or minus 1 to sort of disambiguate quadratics, and then you're also allowed to use sort of, and you are allowed to use sort of cube roots of unity to disambiguate, which is probably not a word, cube roots, like then you also have 6 roots, so you may as well sort of. So those are sort of the things you're allowed to use in this formula, and you get such a thing. There's also a quartic formula. So again, so now you're allowed to use like 4th roots and sort of also 4th roots of unity, but there's no cubic formula. Or sorry, no quintic formula. And in fact, there's no sort of n-tic formula for any n greater than or equal to 5. So, or n-tic. And so there's no general formula for the roots of a degree 5 polynomial using sort of just sort of nth roots. Sorry, let's say iterating nth roots just by iterating. Yeah, let's say just using nth roots and field operations on coefficients. So in here, I'm allowing you to sort of like first take an nth root, then like sort of do some polynomial in that nth root, and then take like an mth root, and sort of, and still like there's nothing you can do. And so here, I mean, like it's not just you want to take square roots of the coefficients, like you want to sort of be able to take square roots like expressed in the coefficients, just like in the quadratic formula. So this is what we're going to show. So we'll make this more precise. And then we'll actually show something stronger. Using Galois theory. And maybe, well, I'll at least sketch all most argument, at least part of the argument will sort of be on your next homework. So that's what we're going to do in the rest of class today. But why don't we go ahead, and before we get started on that, let's take a break till 1:10. Right, so we're sort of on this issue of solvability in radicals. And so let me make precise what I mean when I say a polynomial is solvable in radicals. And it's a little bit different than saying there's no quadratic formula. So I'll also have like no quintic formula. So let me say that, and I'll say what the relation is. Definition. If K is a field, and f of x is contained in K of x, then f is solvable in radicals if the splitting field, so if a, yes, how do I want to say it? Let me say it this way. So if there is an extension L over K, where F splits, and such that there exists a chain of extensions K contained in sort of L, so it's like K is equal to L0, it's contained in L1, it's contained in L2, and so on. It's contained in Lm, it's equal to L. So anyway, yeah, in this to me, saying F splits it here means F sort of splits the linear factor. So L contains a splitting field of F, but it's convenient to, somehow we want to allow L to also be bigger than a splitting field for what I'm about to say. Such that Li is equal to sort of Li minus 1 adjoins sort of square root of something. So an nth root of something. So sorry, not n, any. So some a in Li minus 1 and k. So here, we allow sort of a to be equal to 1. So like if a is equal to 1, that just means we're sort of adding a root of unity. So just like we sort of need not just take like square roots of the coefficients, but we also sort of need to allow roots of unity when we are sort of doing the quadratic formula and sort of the, and like sort of somehow like saying you're adding roots of unity is just saying, saying you're adding roots of unity is just saying, like instead of adding one square root, like allowing yourself to use roots of unity, like instead of adding one square root at a time, you'll sort of like add all the square roots at once. Okay. I mean, that's how we're going to use it anyway. Okay, so that's the definition. I mean, and like, why does that make sense? Well, I mean, that means like, and like if F is solvable in radicals, then sort of for any root, then sort of any root is sort of gotten by sort of iterating iterating ring operations, so gotten from the coefficients. So you can get from the coefficients of F by iterating ring operations and roots. Say radicals instead of roots. So radicals just means sort of like nth roots. And the point is, if you're solvable in radicals, that means the roots live in some field where everything in that field can be expressed sort of by taking sort of some property of taking coefficients and then taking roots. Okay, and so let me say the main theorem. If F is a separable polynomial, then F is solvable in radicals if and only if the Galois group of F is solvable. So there's some convenient terminology. That might not be a coincidence. So recall that means So G is solvable. So group is solvable if there exists 0 a chain of normal subgroups. So this is any element. So, and we had some equivalent formulations of being solvable. You could sort of define it in terms of like the, I can't remember what it's called, the derived series. So there's sort of this and there's some canonical choice of sort of like the smallest possible subgroups such that the quotients are going to be a billion. So let me say finish it. So I'm going to actually use the equivalent definition, where I'm going to require that the quotients are cyclic. And you could just ask them to be a billion. I mean, somehow, as soon as you sort of have some chain where the quotients are a billion, well, I mean, then somehow you're and then like abelian groups can be decomposed into cyclic groups. So by taking a chain of quotients, so just to refine it. And then this definition in terms of the derived series was just there's sort of a canonical like way you can set the series where sort of at each step you're going down as far as possible. Sort of, and if you want to get an abelian quotient, like there's sort of like a maximal abelian quotient. So you sort of go to the maximal abelian quotient, then sort of look at that subgroup and go to the maximal abelian quotient of that, and so on. So that was using this commutator subgroup. But here, this is sort of the format we want it. So that's a statement. And so just like as an example, before we prove the theorem, and before we talk about the proof of the theorem. So x to the fifth. This might not be true if I get the minus on the wrong way. So let me make sure x to the fifth minus 6x plus 3. So the roots of x to the fifth minus 6x plus 3 are not let me say it this way. Yeah, we'll use it the same. So this polynomial is not solvable in radicals. Because last time we saw that its Galois group was S5. Which is not solvable, which we saw very long ago. This is not solvable. So the central series is, or the derived series is Sn S5 contains A5, and then A5 is simple. So the commutator group of A5 is just the trivial group. So the fact that S5 is not solvable just follows from simplicity of A5 and the fact that A5 is not abelian. Okay, so yeah, so last time, what was the argument we gave? Just to recap, we saw S to the 5 minus 6x plus 3 had Galois group S5 because, well, it was irreducible by Eisenstein. The simple degree argument sort of Legendre's theorem gave us that there was an element of order 5 in the Galois group, so that had to be a 5 cycle. Then we sort of looked at, you sort of used the intermediate value theorem and the mean value theorem to see that complex conjugation gave you a transposition, because there was just there are 3 real roots and 2 conjugate complex roots, and sort of together that gave you all of S5. So that was the argument. Okay, but then it's not solvable. So I mean, corollary of this, there is no quintic formula. because if there were sort of a formula that expressed I mean, somehow if there were a formula that expressed the roots of every polynomial, sort of using sort of just like some general equation in radicals of the coefficients, like then it would, in particular, would apply to this polynomial, and well, it doesn't. Okay, so but I mean, like somehow this is, I mean, this is stronger. Like giving a specific polynomial whose roots are not expressible in radicals is stronger than they're saying there's no quintic formula. Like somehow, like it could a priori be possible. So yes, let me sort of say this out loud, and probably not too important to write down and get into, but I mean, it's a priori possible that there is no sort of uniform formula for expressing the roots of all quintics in terms of radicals, even though like if you take any individual quintic, it is possible to sort of express its roots using radicals. I mean, somehow this is like and so, just for example, I mean, like, and this really depends on the base field, right? I mean, like, if I like, certainly there is, and there's no quintic formula over the complex numbers. Like there's no sort of formula. Yeah. So okay. So yeah. So I mean, and there's no formula. So yeah. So it's sort of separately from this. This sort of so separately from this statement, you can show there's sort of no quintic formula, sort of giving a universal way to express the roots of a polynomial, a degree 5 polynomial over the complex numbers, just sort of using radicals of radicals and roots of unity in the sort of coefficients. Like what that means is sort of if you treat the coefficients in variables, if you treat the coefficients as variables, like sort of, well then sort of you're really looking at like an extension of sort of some function field and like sort of the number of variables equal to the number of coefficients. And you're sort of looking at sort of the universal sort of quintic over that. And like, and basically what you showed on your homework that's due, one of the problems on the homework that's due, due next Thursday now. Basically what you're showing is that Galois group is Sn. So sort of that tells you that there's no quintic formula sort of over any field. But it is true that like if you take a quintic polynomial over the complex numbers, then it's solvable in radicals, because I mean, you don't need radicals at all. I mean, sort of all of its roots are complex numbers. So and somehow like these are sort of different statements, and this is really sort of like somehow maybe a stronger statement. So and conversely, sort of there are fields like, yeah, and like another, and there are fields that are not sort of algebraically closed, which is true. Like over a finite field, if you sort of take any given polynomial, like its splitting field is an abelian extension. So like, and somehow you can express it. You can express the roots using radicals, because in fact all of the roots are sort of roots of unity. So somehow, and like there's some, and yeah. So just I want to emphasize like there's some ambiguity towards what you mean by something like this, but like maybe the strongest type of counterexample you can give to not having a quintic formula is there's like exhibit specific polynomials over a field that don't have, with the caveat that sort of there are some other ways you can interpret it, and like, well, depending on your field of base matters, and yeah. Anyway, and this is sort of a very strong way to say there's no quintic formula. By giving us this one, and sort of in the example, and there is no entic formula, because I mean last time we saw how to construct extensions, so for n greater than or equal to 5 of Q with Galois group S5. So this was this thing about sort of choosing some polynomial mod 2, mod 3, and mod 5, and then sort of applying the Chinese remainder theorem to get something with Galois group S5. And so this is we had some small gap in our proof because we didn't sort of justify this algebraic number theory statement we need. But and the gap is not so small, and so it's not so hard to fix. And you can take this as a fact that there are sort of Galois groups. There are sort of extensions of Q with Galois group Sn for an arbitrary n, and for n greater than 5, those are not solvable. Okay, so and what's the idea of this? Yes, let's do the easy direction to prove this theorem first. Okay, so let's first suppose so and the easy direction is if you're solvable in radicals, then the Galois group is solvable. Okay, so if F is solvable in radicals, then we have yeah, okay, good. So if F is solvable in radicals, then we have means we sort of have this extension. So, right, this extension up here. So LM is equal to L, we'll call L. So we have this extension L over K that sort of breaks up into these sub-extensions where LM, so LM is equal to so LI is equal to LI minus 1, sort of adjoin sort of K through of some element. We call it little L sub I minus 1. I guess I'll call this K sub. Yeah, sorry, let me write this so I'm not writing I minus 1 everywhere. I'll write this as Li plus 1 is equal to Li adjoin AI 1 over Ki. Okay, so well, first observation is like, let me just make L much bigger. Like, and so I'm going to make L bigger, and L. So and here it doesn't say L is Galois. Maybe L is not Galois. But I mean, basically, I can make L as big as I want and make it Galois over K, and then so let me sort of I can make L bigger than Galois over K, then show sort of Gal L over K is abelian, which will imply sort of Gal F is solvable. So imply that the Galois group of F is solvable. Okay. Because it's a quotient. And so L contains a splitting field. And L contains all the roots of F, so L contains a splitting field for F. So when I say the Galois group of F, from now on, I'm going to mean that specific splitting field. Okay. Good. So that's the idea. And how can I use that sort of fruitfully? Well, in taking roots is sort of a little bit bad because it might not, these might not be Galois extensions the way I've set this up. But let me just add in. So let me take L to be equal to let me replace L. How do I want to say this? Okay. Yes, let's take. So I'm going to replace L with some field. I'll call it M, capital M, which is just L. And I add all of the so I'll add some new capital K. So this is capital K fruits of unity. So where K, well, the product of all of these Ki. So I want to render myself into a situation where when I extract one root of unity, I'm extracting all of the roots of unity. And so in particular, I'm sort of getting a Galois extension when I extract, when I extract one K fruit, like when I extract the Ki fruit of AI, I'm getting a Galois extension. So that's what I want to do. And so in order to do that, let me just sort of take all the, let me just sort of add in enough roots of unity to make that happen. So that's what I'm doing here. Okay, and then so I'm going to write so K is contained in the thing where I take sort of, I have too many capital Ks. So this will be a lowercase k again, sorry. So it'll be the product of these Ki, which are sort of the powers I added. Sorry, I bad choice of variables, my bad. Okay, and so, well, K is contained in, I just take K and I add all sort of these roots of unity. And then this is contained in L1, sort of add all these roots of unity. So all my less than equals are supposed to be contained in. Okay, so but anyway, this extension is really Galois and sort of you can check that this is Galois. That's probably not quite right. I should be careful. I think, yes. Okay, let me be careful for a second. So let me sort of say what we definitely know for sure. And so this, I'll call this sort of, so K is equal to M. 0 is contained in M1, it's contained in sort of M2. M sub little m is equal to M. Okay, so I've replaced these this chain, but now sort of, and then I still have M I plus 1 is equal to Mi. I extract a sort of Li to the 1 over K. So I extract K through. But I mean, now the point is this is Galois. Each of these extensions is sort of Galois. Okay. And sort of not only is it Galois, so in the Galois group of Mi plus 1, over mi is equal to this is equal to so this is contained in z mod kz. So this is sort of an exercise on your homework. It's sort of not quite so the same way, but the point is, if you already have the k-fruits unity, it's like z mod kiz. If you already have the k-fruits unity, then when you sort of take a k-fruit of something, now that extension is Galois, and the Galois group is sort of z mod ki, this is contained in z mod kz. Okay, so okay, and so this is almost what you want, except I haven't sort of justified. I haven't justified that m is Galois. So that m is Galois over k. And so this is a real issue because, I mean, it's not true in general. Like this and sort of such a thing won't be Galois, and somehow, like you've probably seen this on your homework already, depending on how far you've gone on it. But like you can sort of take two square roots in a row, and then end up with an extension that's not Galois. So so in fact it might not be. And if it were Galois, then this would sort of give you your sort of sequence, and this would give you the Galois group is solvable. So you'd sort of just take the sort of subgroups corresponding to these, and then each quotient would be z mod mz. But you can sort of modify this. So you can modify this. And essentially, so sort of at each step, so you don't want to just take the root of Li. You want to take all the conjugates of Li. So that's sort of the issue that's sort of making this not Galois, is that sort of at each step, like you sort of just picked one thing, you took a k-fruit. I'm like, well, that sort of sub-extension is Galois. Like if you apply sort of field automorphism to the whole thing that sort of moves Li to something else, then sort of you might not have sort of like the square root of the thing it moves Li to. So like sort of you just sort of by so at each step you're going to sort of have these. So you want to sort of show iteratively at each step sort of your Galois, and then you get a new Galois extension, which when you sort of instead of sort of just adding sort of Li, you sort of add all the conjugates of Li sort of for the Galois group up to that point. And then once you but then so okay, but you're still going to get an abelian extension because somehow like sort of taking nth roots of all of those conjugates is just sort of the compositum of a bunch of abelian extensions. And sort of if you take a composite of extensions, like then the Galois group is sort of a subgroup of the product. So I mean, this is yeah. Well, okay, I only have 2 minutes left, so and obviously I didn't set myself up to sort of do this carefully. So in the exercise for you is then to do this carefully, but it can be done. And it's sort of a nice exercise in sort of thinking about this issue. It's a nice exercise in thinking about this issue that sort of like taking a Galois extension, I think a Galois extension of a Galois extension, sort of the total extension might not be Galois. So it's sort of a nice chance to work with that idea. Okay, so that gave, okay, so this was the easy direction. But somehow the hard direction is not, I mean, the hard direction is only harder because it requires some input we haven't proved yet. Like, it is actually simpler, like it's sort of simpler to write down than this, and also like we saw the main idea in it. So the hard direction if G is solvable, then sort of L, then F is solvable in radicals. Okay, so step one, just add in all of the add in all the roots of unity, sorry, of order dividing G. And I'm so okay. So I mean, both here and before, I've sort of, and I guess the way I've sort of presented this proof, I've sort of been ignoring this issue of whether F is separable or not. And well, and that's really an issue just in characteristic P. So I haven't been very careful about what's going on in characteristic P. So you should probably sort of treat the proofs as I've written them as sort of valid in characteristic 0, but you have to be a little bit more careful in characteristic P. Okay, let me forget about that for now. And so it's just because sort of like you need to sort of explain why you don't need P roots of unity, or sort of like, or sorry, I mean, that's not quite what I mean, but so in the next sentence, you need to sort of say something about that. So step 2. So yeah, this is really the step where you need to do something else, something extra in characteristic P. Use Kummer theory. So this says if K contains nth roots of unity, and L over K has degree n, so it has Galois group. So L is an extension of K that's Galois, and it has Galois group Z mod NZ. Then sort of L is equal to K is gotten just by sort of taking an nth root. So this is sort of, so the statement sort of is much more difficult than the other direction. I mean, sort of the homework problem where you sort of show if you have the roots union, you add such a thing and then show this Galois group it sort of contains Z mod NZ, like that's not so hard. Here, like it's a little bit, it's sort of a much stronger statement to say if the Galois group is Z mod NZ, then in fact you were obtained in this way. But this is sort of what Kummer theory says. And so this will be, and this sort of ties in nicely with some representation theoretic ideas. So this will be on the homework, on the next homework. So this is, so the only caveat here is, and I should have said, n coprime, this n here should be coprime to the characteristic of K. So if sort of you have a Z mod NZ extension, sorry, and positive characteristic, and sort of K has positive characteristic P, then so you need something also and somehow you need sort of Arndt-Schreier theory to sort of study this. Just something else. So okay, so anyway, maybe the point is really sort of you should treat this. Let me just say this. Let's say the characteristic of K is 0. I mean, sort of to some extent you can salvage this, but I should have. You have to be a little much more careful to salvage this and to salvage what you want to say and what precisely you want to say when characters of k is not 0. Let me sort of not. Okay, but yeah, so sorry, I'm over time, so let me stop there. But so the point is, it's the exact same. Like, if you're a solvable group, like you should just take, sort of add your roots of unity. Like that only makes your Galois group sort of a quotient, so it's still going to be solvable. And then it's about like add the roots of unity. You're still going to have a solvable Galois group. And then once you've done that, like then sort of just take sort of the fixed fields for this chain of subgroups and apply Kummer theory to see each of one of them is gotten by adjoining a root. So that's sort of the idea. Right, but let me stop.